This is Inequalities and Systems for Pre-Calculus Math 11. Today we're taking a look at solving systems of equations. Basically, when we are trying to solve a linear quadratic system, so that's one of the equations is a linear equation, the other equation is a quadratic. The solution is always given as an ordered pair. Now, if we remember what an ordered pair is, that's basically just an xy coordinate. The system of equations may have up to two solutions. So what are our options? We could have no solution. So let's draw a parabola. It doesn't really need to be very exact here. There's a parabola. Let's draw a line which doesn't pass through that at all. Okay, that's pretty straightforward. We can just draw a line like that. So that has zero solutions. We could have one solution. So let's draw a parabola right there. One solution would be, okay, it just comes in and just clips it right on the edge just once, and we end up with one solution. And how about two solutions? Well, let's draw a parabola. Let's have this one opening down. The line comes in and cuts it through two spots, and we have two solutions. So those are the three different options we have for the number of solutions. Either it's no solution, one solution, or two solution. Now, solving these systems algebraically, fairly straightforward. It's really a matter of grouping like terms and factoring if you need to. So let's do that. We're going to equate the two equations. So if you think about linear systems, we've done substitution, you've done by comparison, that sort of thing. Similar thing, or addition, subtraction, similar thing here. We're just going to make them both equal the same number. In this case, they're both equal to 0. And instead of just saying, okay, well, they're equal, we're going to end up with a y and x value, let's actually solve for y in these equations. So we have equation 1 here, equation 2. So let's work with a little bit with equation 1 first. X squared plus 4 equals 2y. X squared plus 4, we'll divide both of those by 2. Half x squared plus 2 equals y. There's equation 1. Equation 2, let's solve that for y. We have x plus y minus 2 equals 0. Y equals, basically just subtract x and add 2. There's the other equation solved for y. So what we can do now is we can equate these two. They both equal y. Notice that we have this equation equaling y, and we have that equation equaling y. So they both have to be equal. 1/2 x squared plus 2 has to be the same as negative x plus 2. And we'll notice that we can cancel a positive 2 from both sides. And if I add that x over to the left-hand side, I get a 1/2 x squared plus x equals 0. Now the way we're going to go about this is to factor. Usually, if it's a quadratic, we'd have to factor a quadratic trinomial. In this case, it's actually just two terms, so we can actually just pull out the greatest common factor here, which is a 1/2. Sorry, greatest common factor is x, and we're left with 1/2 x plus 1 equals 0. So what happens is these two things separately have to equal 0. So x has to equal 0, and a 1/2 x plus 1 has to equal 0, which gives us a solution of negative 2. So we have two values here. We have x equals 0 and negative 2. That's the x coordinate of where these two graphs cross. One's a parabola, one's a line. We have two solutions here. Great. We still need to find the y values though. So let's go into a little table here kind of thing just to break it up a bit. Let's take a look at x equals 0. We can plug it into either equation. I'm going to plug it into the line just because it's a little bit easier to work with, less squaring, no fractions. 0 plus y minus 2 equals 0. So we get y equals 2, and that ordered pair is 0, 0, 2. Try the other one. We have negative 2 plus y minus 2 equals 0. Y minus 4 equals 0. Y equals positive 4, and we have a solution of negative 2, 4 as our other ordered pair solution. So we're trying to do this algebraically. We don't want to have to graph this. Graphing gets to be a little tedious, and that's what we do. Solve for y or x. In this case, I solve for y. Equate those two equations, determine the x values, and from there determine the y values. Not much different here when we talk about a quadratic system, two parabolas. Solution to a quadratic system of equations is also an ordered pair, also an xy value, that also satisfies both equations, meaning you can plug it into both. The system may have, and here's the interesting part, up to infinite solutions. Now, a little bit careful, it's not up to 0, 1, 2, 3 all the way up to infinity. There's just special cases. We could draw a parabola opening up, one way over here opening down. Clearly no solutions. We could draw parabolas with one solution. One of them's opening up, let's say, the other one opening down, exact same vertex. Why don't you try drawing a parabola system, a quadratic system with two solutions. Let's say one opening up, one opening down, crosses twice, two solutions. So what's it going to mean if it has infinite number of solutions is that we draw one parabola and the second equation that we're given is basically the exact same parabola. It's right on top of it. So not as interesting, but it is possible to draw two parabolas, get two equations which may not look exactly the same that give you the same parabola. So let's solve a system algebraically. We have a parabola. So we have a parabola, y equals negative x squared plus 8x minus 15, and we have a second parabola. They're both equaling y already, so why don't we just equate them right from the start here. X minus 3 squared. We've dealt with similar problems to this algebraically, expanding grouping like terms. Let me do that. Negative 8x minus 15, and on the right hand side we have x squared minus 6x plus 9. That's foiling the binomial out. Let's group like terms. I'm going to move everything over to the right hand side because I like having my x squareds positive. X squared over makes it 2x squared. Subtracting 8x gives me negative 14x, and adding 15 gives me 24. So we're trying to solve this. It could be a quadratic equation situation that we have to use. Let's see if it factors. I notice that a 2 will factor out of everything. That usually makes it a little bit easier. If you can't see this factoring, you know what, go ahead straight away, use a quadratic formula. That's fine. I notice that this does factor nicely into x minus 2. Oh no, x minus 3, sorry, and x minus 4, which tells me we have x solutions of 3 and 4. So let's build our little table again to find out y values for these. X equals 3, x equals 4. I don't know, let's plug them into the y equals x minus 3 squared. It's a fairly simple formula. So y equals 3 minus 3 all squared, y is 0 squared. Oh look, y is 0, and we have an ordered pair of 3, 0. We'll go into the same equation, let's say. 4 minus 3 squared, 1 squared is 1, and we have the ordered pair of 4, 1. If you want to really be precise here, I'm going to put this in green just to show you. That's not overly necessary, but you can do this if you really want to check your answers. You're going to plug these values in. Let me just do it for the 4, 1. Check in the other equation. So what I used is I used the y equals x minus 3 squared. Let's actually check it in the y equals negative x squared plus 8x minus 15 equation, and see if it holds true for that. 1 equals negative 4 squared plus 8 times 4 minus 15. So we have negative 16 plus 32 minus 15. Turns out that negative 16 plus 32 minus 15 is 1. So great, that that works. So what's the techniques we're talking about when we're talking about solving systems of equations? Much like a linear system you saw in previous grades, we are going to use by comparison. We're going to solve for one of the variables, usually y is the easier one, and make those two equations equal. This ends the notes for solving systems of equations, section 5.5.